Today we're going to start on the second part of the course where we talk about complex asymptotics. This is a set of methods that we use to extract information about the coefficients right from the generating functions. Again, as in the first part of the course, we want high-level automatic methods that get us to the results that we need. And we'll try to introduce that in today's lecture. So let me just start off with a roadmap of what we're going to talk about before getting into complex analysis. This is our standard overview, and again we've finished the first part of the course on the symbolic method, and now we're going to start into complex asymptotics, where again we're going to have talk about machinery that we can use to take a generating function equation and get out asymptotic estimates of the coefficients automatically. Today we're going to talk about rational and meromorphic functions, and we'll talk about what those are in just a minute. So our starting point is that with the symbolic method, we saw that we had tools, combinatorial constructions, and transfer theorems that give us generating functions that vary widely in nature. That's the generating function for derangements, that's for involutions, that's for surjections, and so forth. And these functions are all quite different in character. But still, what we want to do is, eventually, our goal is to get asymptotic estimates of the coefficients out. So we want to know that the probability that a permutation is a derangement is about 1 over e, and so forth. And we'll see during the second part of the course, for all of these functions, we are able to automatically extract these kinds of asymptotic estimates. Now, the classical approach is to take the generating functions and derive an explicit expression and then use asymptotic techniques to develop an approximation. But with analytic combinatorics, what we're going to do is directly derive the approximations. So this is an example that I've used in the very first lecture, but it's worth pointing out again. When we're counting, say, Catalan trees, we have a construction that gives us a generating function equation. We get an explicit form for the ordinary generating function. We can use Newton's binomial theorem to expand it. And then extract coefficients, and then we can use Stirling's formula to get an approximation. And I've left out a lot of calculations in this derivation, and you saw them in earlier lectures or in part 1. Or for derangements, similarly, we have a construction that gives us an EGF equation. It's a relatively simple explicit form of the exponential generating function. And that one we can also expand, but now that's a convolution, a double sum, but we can manage it, get an explicit form of the coefficients, and then eventually see that that approximates to about 1 over e. But we've got mathematical arguments in each one of these steps to make that we don't want to repeat these arguments for every problem that we encounter. And not only that, the combinatorial constructions that we use in the symbolic method, both through unlabeled and labeled objects, the whole idea is that we can use those same constructions to make variants of the objects that are much more complicated and get quite complicated forms for generating functions. And then we get actually fairly complicated functions that might lead to difficult problem extracting coefficients. And certainly in classical analysis, these kinds of problems face mathematicians all the time. But as we'll see, starting in today's lecture and in the next couple of lectures, there's an opportunity, because in the end, it turns out there's a relationship between the generating function, the explicit form of the generating function, and the asymptotic result. And even in these two examples, you can kind of see it. There's a square root in the explicit form for Catalan trees, and there's a square root of n cubed in the denominator in the asymptotic approximation. There's a e to the minus in for derangements in the generating function. There's an e to the minus in the asymptotic result. And as we'll see, that's no coincidence. So here's the overview of really what we're going to want to be doing for the next several lectures. In the first part of the course, we talked about the idea of taking a specification and using a symbolic transfer theorem to give us a generating function equation directly from the specification. In this part of the course now, what we're going to do is take the generating function equation and develop analytic transfer theorems that immediately give us the asymptotic result. And we'll see many, many examples like this character where the derivation of the asymptotic result is as simple as that. Specify, transfer, transfer, asymptotic result. We'll see many examples of that. So that's our overview. This really represents a profound shift in the point of view. In the first part of the course, we were treating generating functions as formal objects. It was all about symbolic manipulations to have some kind of formal relationship between the specification and the generating function that led us to the generating function equation. Starting with George Polya many decades ago, some mathematicians started to realize that we could also treat generating functions as analytic objects, a completely different point of view. And they're the same function, and we need some rigorous justification of it, but in the end, that's how we get our asymptotic results. And the other thing that is going to come up starting in today's lecture is that we're not going to stick to the to real value generating functions. We're going to move to the complex plane. But an analog to real valued functions is worth considering. So what happens, say we have this generating function 1 over 1 minus 2x, that's a generating function that counts the bit strings. What happens if we treat that as a function? Well, the coefficients are positive, so we only have to worry about the positive part of it. And we have this idea that we can use a series that's valid in a certain interval that allows us to extract the coefficients and get the answer that we want. In the case of this one, the Taylor series of that function analytically is the series 1 plus 2x and so forth. That's only valid for x less than 1/2 in this little interval here. But that validity is enough to give us what we need. When we take the coefficient of z to the n in that, we get our result z to the n. Now, but there's other things that we can do analytically with these types of series. So, for example, we can differentiate term by term where the series is valid. And that's a analytic manipulation that also corresponds to formal manipulations on the generating function. And then we have the idea of a singularity. There's a point where that series is no longer valid. In this case, when x equals 1/2. So we have to recognize these points and not try to do analysis at on the series at points where the series is not valid. But we have the idea of continuation. We can take that function and we can use that function even in places where the series is not valid. So in this case, like we could say f of 1 equals -1 just by plugging in x equals 1. And in the whole positive plane, actually everywhere but at the singularity, we can compute a value of the function. And through continuation, then we're opening up more analytic manipulations that we can do to get the results that we want. And the same thing happens in the complex plane. When we assign complex values to a generating function, we have a more complicated kind of plot. It's a two-dimensional thing that I'll talk about soon. We still have the idea of a singularity. We still have the idea of a series representation that holds in a certain domain and allows us to extract coefficients. And we still have the same useful concepts. We can differentiate, we can identify singularities, and we can continue to places even where the series might diverge. So all of those same basic concepts are useful even in the complex plane. And if you're not familiar with complex numbers, don't worry. I'm going to try to give you the concepts that we need in this lecture from first principles. But really, I want to talk about complex values in this opening segment because there's really a surprise that happens when we look at generating functions as complex functions. And in fact, the surprise is that all we need to look at is the singularities, and actually usually just one, to get full information on the growth of the coefficients. as Philippe says, singularities provide a royal road to coefficient asymptotics. There's no real reason why this should be the case. It's serendipitous. We have this thing that looks like a function. Let's treat it like a function on the complex plane. Our coefficients were supposed to be counting things. Why should a complex variable have anything to do with it? A complex variable has really a lot to do with it, as we see, and it provides, that analytic point of view provides a mechanism where really we can gain full understanding of the counting problems that we started with, even though at the start we were working with generating functions just as formal objects. And at the end we're going to work with them as complicated functions in the complex plane. So in general, as we'll see, what's going to happen is that the combinatorial generating functions that we're examining, they're functions in the complex plane with positive coefficients since we're counting things. They have an exponential growth factor and a sub-exponential factor. And the first principle is that it's where the singularities are that dictates the exponential growth. And that's not too difficult to see, and we'll see it specifically in many examples even today. In the sub-exponential factor, that's our second principle, is the nature of the singularities dictates what the sub-exponential factor looks like. Depending on what those singularities are, and there's different kinds of singularities in the complex plane, and we'll talk about that in some detail. Not too many different kinds, but a few different kinds, and whichever one it is, that's what dictates what the sub-exponential factor looks like. So just as a preview, and again, I haven't defined really what the singularities are, the types of generating functions, but anyway, it's worth showing how things distinguish themselves. So for example, the generating function that counts all the strings with no 0, 0 is that function there. We saw that in the first lecture. That's called a rational function, and the first thing we're going to look at is rational functions. Its singularities are called poles. So poles, the location of the singularity gives the exponential growth. And because it's a pole, it's got a constant sub-exponential factor in this case. For derangements, it's also a pole. Its location's at 1, so its exponential growth is 1 to the n, which goes away, and that's the sub-exponential factor, again, is a constant. But for Catalan trees, it's got a different kind of singularity, and so it's got a different nature of its sub-exponential factor, and we won't see those for a couple of lectures. I forgot to mention that derangements, the kind of generating function that is called meromorphic, and that's the second kind of generating function that we're going to look at today. So that's a quick overview of how we're going to approach the idea of automatically extracting coefficients from generating functions. Next, we'll dive into first principles of complex analysis.